right, why certain elements form certain ions can be explained by looking at their electron configurations. So the important thing to know about this is that full or half full subshells are particularly stable. Okay, and the reason for that is that's due to parallel spins. Okay, so this brings us into a discussion of our fourth quantum number. So we've known about our quantum numbers. We talked about those in the end of the last chapter. And we have N, we have L, and we have M sub L. And our fourth quantum number is M sub S. Okay, M sub S is the spin number. Right? And electrons have spin. They either spin one direction or they spin the other. And by convention, we talk about it spin up or spin down. Okay, so your options for the M sub S are only two, plus a half or minus a half. Okay, and that is relating to spin up or spin down. Okay, so this is how no two electrons will have precisely the same set of four quantum numbers. Because even if the first three numbers are exactly the same, which is possible, your last number, the M sub S, will either be a plus a half or a minus a half. No two electrons should have exactly the same four quantum numbers. Right, now let's take a look at how this sort of plays out. And we're going to talk about drawing the electrons in boxes, which is part of your homework. So let's use bromine as our example. So bromine's electron configuration is argon 4s2, 3d10, 4p5. Right? So if I draw this out, and I can use boxes to represent each set of orbitals. So I'll have one box for my 4s, because s only has one orbital. It's a sphere. And then my d's, I'll have 5 boxes because there are 5 d orbitals. So here's my 3d. And then my p's have 3 orbitals, so I'll have 3 boxes. Okay, so I'm going to fill these with electrons, and I'm going to use arrows. And my arrows are a little bit stylized, but you'll be able to tell what I'm drawing here. So each individual orbital can hold 2 electrons at the most. But I'm going to fill each orbital with 1 electron before I put a second one in it, right? And the 2 electrons should have opposite spins. So there are 2 electrons in my 4s, so I'll have 1 spin up and 1 spin down. Then my d orbitals have 10 electrons, so I'm going to fill each orbital with 1 before I come back and start pairing them. So here's 1, 2, 3, 4, 5. Now I'm going to go back and start pairing them. 6, 7, 8, 9, 10. Okay, now my p's, I'm going to do the same thing. There are 5 electrons in my p's. I'm going to fill each box with 1 before I come back and start pairing them. So I'll have 1, 2, 3, 4, 5. All right, now, my d's have 2 sets of electrons that are all parallel spin. I've got 5 that are spin up and 5 that are spin down. All right, so 2 times the parallel spins right? Very stable. In fact, it acts like a core. Okay, our core here in bromine is technically just the argon. But those 3Ds, being a completely full 3D, are so stable that they act like core electrons. They're actually on the inside of the atom. Right? Our 4s and our 4p are larger, so they're actually on the outside. So my stable 3Ds are so stable that they actually act like core electrons. Now, with my 4p's, if I fill, I get a completely full p orbital. Very stable. Right? So if I make this a bromine minus and add one more electron, now I have a completely full p orbital, 2 times the parallel spins, and I get Br minus out of it. Okay, this is why bromine doesn't make a 2 minus or a 3 minus, because it only needs one more to get a completely full p orbital on the outside. All right, let's look at things from the other direction. Let's look at sodium. Right, so sodium, its electron configuration will be helium 3s1. Okay, or to expand that so that I can draw it more clearly, I have 1s2, 2s2, 2p6, 3s1. Okay, and excuse me, it's not helium, it is neon. My mistake. Okay, so this part right here, that's the neon. All right, so let's draw the boxes for it and see how things play out. So my 1s, s has one orbital, so I get one box for the s. My 2s, my 2p's, there are 3 orbitals in the p. And then I've got my 3s box. All right, so let's go ahead and fill in our electrons. My 1s has 2 electrons, spin up, spin down. My 2s also has 2 electrons, spin up, spin down. My 2p has 6 electrons. I fill each one individually, then I pair them. And then my 3s has 1 electron. All right, so notice that my 2p is a full subshell. Right, so if I get rid of this one, I get to that full subshell. Right, so this is why sodium gets rid of 1 electron and not 2, 3, or 4. Because if it gets rid of 1, then it has a full subshell, which is particularly stable. Right? So to make Na+, we get rid of 1 electron to get that full, completely full p subshell. All right, so our next topic is called ionization energy. Or just IE. All right, and what's interesting about ionization energy is that Zeffective, once again, drives the trend. Okay, so ionization energy is the energy to remove an electron, energy needed to remove electrons. Okay, it always takes energy, right? Ionization energy is always positive. Okay, we'll never have a negative ionization energy. It always costs energy to remove electrons. All right, so the rigid definition, the equation definition, would be, for example, to take a gaseous atom and always a single atom. And the reason for that being single atom and always gaseous we'll approach in chapter 9 when we start talking about lattice energy. But we'll take a single atom in the gas phase and we'll remove an electron to make it positive, ion in gas phase, plus an electron. Okay, and it'll have an enthalpy attached, a delta H, which will be the ionization energy. And we'll say IE1. Okay, so that's referring to the energy to remove the first electron. Okay, so the important consideration here how stable are the electrons? Okay, very stable electrons will require a lot of energy. Unstable electrons, it'll be easy to remove. Okay, so how does Zeffective relate to this? So Zeffective is the effective attraction between the nucleus and an outer electron. So if that attraction is very strong, it's going to take a lot of energy to remove that electron. Okay, so the ionization energy trend is the same as the Zeffective trend and atomic radius. Okay, so the general trend in ionization energy is the same as Zeffective and the same as atomic radius. So left to right, ionization energy goes up. Okay, so as Zeffective increases, it costs more energy to pull off an electron. Okay, and then top to bottom, ionization energy goes down. Okay, and the reason that it goes down is that our radius is getting larger. Electrons are farther away. So easier to remove. Okay, so when I say that it's the same as Zeffective and atomic radius, those things all track together. So as atoms get smaller, Zeffective is increase. Okay, and as electrons are closer and held tighter to the nucleus, it costs more energy to remove them. Okay, so ionization energy goes up with smaller atoms with higher Zeffective. Ionization energy goes down as we go top to bottom because our atoms are getting larger and larger and larger. The outer electrons are farther away, so it's easier to pluck one off. Okay, I'm going to go ahead and stop here, and when I come back, we'll talk about in more detail the trends in ionization energy.